Let's finish up the last topic in chapter 2, and we'll be starting chapter 3. Buoyancy. You know buoyancy. Float on your back in your swimming pool or the ocean, float on your back. You're buoyant. So, let's talk about buoyancy a little bit. Everybody has good intuition about it, but you know, if cup of water, I'm not drinking. I'm not going to do this today. It's not that bad a day Monday, but I'm not that desperate. Golf ball. This is down the bottom. Ping pong ball. It floats on top. They're roughly the same size. Why does one sink? Density and the weight. That's right, it's the same volume, so density or weight. What makes ping pong ball? It's not halfway down even. It's not halfway down. It's mostly floating. It's into the water way down here. So there's something else acting there too. There's something else acting. What two forces do you think acts on it? What do you think act on it? What two forces?
Buoyancy is one of them.
Okay, and?
Gravity. Yeah, gravity.
Which one's heavier? Well, gravity, yeah. This one's heavier, so this one's lighter. Okay, so that's right, a buoyant force and the weight. If it sinks to the bottom, guess which one wins? The weight. Float on top, what do you have? Buoyant force up, weight down, it's floating on top. Let this thing go in the ocean, it'll sink a long way. Okay? So yeah, it's something about the weight. Well, you know, what causes a buoyant force? You can say buoyant force, but so what? I mean, I could say it's the bazooka force. What's that? A bazooka force. No. Why is there a buoyant force? Well, that's what this picture is going to show you. Here's an object, golf ball, ping pong ball, whatever. The top. Take a slice of a little circular sliver of it. Cheese stick. The pressure up here, not too big. The pressure down here, uh-oh, bigger, we're deeper, bigger pressure, smaller pressure. Which one wins? Bigger pressure. What's the buoyant force want to do? Raise this thing up. What's holding it back? Obviously, the weight going down. So it's like a balance between the weight. If the weight's too big, the thing sinks. When you fill your lungs with air and you float in your back, yeah, that's right. Your density goes down, you have air in your lungs. So yeah, so here's our little circular area, dA for instance. Do it vertically. Here's the free surface. Pressure up here is P naught. The equation, pressure goes up as we go down in the fluid. P naught is the surface pressure at the very top. And this is in your book. I'm just repeating what's in your book, but I want to go through it so you can see it more clearly. The sum of the forces in the z direction due to pressure. At the bottom, big pressure. Which way is that pressure point? You know the rule. Pressure is a compressive stress. It always points on the surface, into the surface. Pressure at the top, minus, pointing down, normal stress. Subtract the two, left this little piece off here, subtract the two. The P naughts cancel out. Rho G times H2 minus H1 times dA, there it is. But notice what the differential volume dV is. dV, the differential volume. It's the area times the height. What's the height? H2 minus H1. So this is like a differential volume. So replace that with the differential volume. So dF of z, this the z direction is vertically in this picture of the vessel. The net force in the z direction equals this guy here. Integrate both sides. Integrate over what? Integrate over the volume, total volume, V. Bring out the constants. We assume incompressible, rho is a constant. We assume G a constant. Integrate dV over V, and we end up with rho GV. So, F buoyancy equal rho GV. What's rho G? Gamma. What's gamma? Newtons per cubic meter. What's V? Cubic meters, newtons per cubic meter, times cubic meters, newtons. Yeah, that's the force, newtons. Okay. What's the volume? It's the volume occupied by the part of the object submerged into the liquid. Acts through the centroid of the displaced volume. To the centroid of the displaced volume. What does displaced volume mean? It means the volume of the liquid pushed out of the way by the object. That's the displaced volume. It's this volume inside that line right there. That's the displaced volume. Oh, you can go through the proof just like we did previously. The textbook doesn't do it. They just say it goes to the centroid of the displaced volume. So, but you can go through all the gory details. Archimedes principle, of course. Archimedes principle from science. So, which way does the buoyant force act? Upward. Okay. What does it act through? The centroid of that volume. Okay, so that's the concept of buoyancy. You've got a couple problems for homework on buoyancy. I'll do an example here. Okay, example. A log. Log floats in water. We're told that 1/4 of its volume protruding above the water surface. 1/4 volume above water surface. What is the specific weight of the log? Okay, so here's our log. 1/4 of it is protruding above the water surface. Draw a free body diagram. Buoyant force force, weight. The weight acts through the centroid of the log. The buoyant force acts through the centroid of the displaced volume. Where is the displaced volume here? That's how much water was pushed out of the way when the log went down in the water. That's called the displaced volume. Where's the centroid of the displaced volume? Right there somewhere. I don't know up or down, but I do know it lies along that line right there. That's why I put FB there, acting through, not through that, there's two things. Okay, the center of gravity and the centroid of the displaced volume. The weight acts through the center of gravity. FB acts through a different place. Okay. It acts through the centroid of the displaced line. Sometimes they're on the same line, sometimes they're not. It depends on the geometry. Anyway, here they are. So, some force in the y direction equals 0. The weight equal FB. Okay, the weight of what? The log. The whole log? Well, of course the whole log. Okay. Gamma of the log times the volume of the log. FB. Here it is. Gamma of what? Well, what did you push out of the way? Water. The volume of what? The volume pushed out of the way. Displaced volume. Gamma of water times the volume displaced. Okay? We want to find gamma. Gamma equal gamma water times the ratio volume displaced over the volume of the log. 62.4 pounds per cubic foot. Now, you have to be careful, of course. Where's the displaced volume? That's the line volume here, the line volume. Where's the volume of the log? That's the circle. That's 3/4. 1/4 is above water, 3/4 is below water. 3/4 is below water. Displaced volume ratio, 3/4. Gamma then comes out to be 46.8. Okay, so you should be able to work the homework. It's pretty straightforward on that topic. You can also get into what we call stability, when something might tip or not tip. Variable, too many people on one side of the top deck or something, and it's a wave that goes over. Why won't it come back and right itself? Well, that's part of the buoyant force. But there's no homework problems on stability, so they're just on the buoyant force. Okay, that pretty much wraps up chapter 2. It's pretty long. We've been in this chapter since the second class meeting about. So yeah, it's pretty long. That's why the first midterm includes chapters 1 and chapters 2, because 2 is such a big, long chapter. Okay, now we're going to move on to chapter 3, but we're not going to have any of chapter 3 on the first midterm. Some people cover the material in chapter 3 later. I'm going to follow the textbook on this one. So we'll follow what's in your textbook. And we're going to look at the Bernoulli equation. All right, I'm going to start off and maybe we'll define a streamline first. Okay, so here's some cylindrical object. And we have flow around the object. So it goes around like this. I won't draw top and bottom, I'll just draw the top, the bottom symmetrical. This is like a piece of pipe in an airstream. When people draw pictures like this, these lines they draw are called streamlines. Definition. The official definition.
Tomorrow. Yeah, do the lab for me.
Okay, that's the definition of streamlines. So, here's the velocity vector at this point. Here's the velocity vector at this point. Here's the velocity vector at this point. Well, you can see what we're doing. You okay, man? Okay. A lot of the streamlines are lines. I mean, do you see them in the real world? Of course not, no. Sometimes you do. You've seen the ads for cars in a wind tunnel with smoke, and you see the streamlines go around the car, follow the back contour, and you break off in the back. Those are those like smoke. Those are streamlines in steady state. So we can see them by adding smoke or hydrogen bubbles to a flow field, liquid flow field, or smoke to a gaseous flow field. But that's what they look like. That's their official definition. We'll talk more about streamlines, path lines, and streak lines later on. But for right now, we're just concerned with streamlines. And we're going to define N and S. N means normal, N direction. S means along the streamline direction. So we attached our coordinate system to the streamline. So S is along a streamline, N is normal to a streamline. So we have two components of acceleration. Along the streamline, A sub S, dV dt, partial V with respect to S, partial S with respect to T, product rule, dV ds, and of course ds dt is just the velocity, and the normal acceleration v squared over r, where r is called the radius of curvature. We're going back to our dynamics background for those two guys. So you can have both. Streamwise acceleration and a normal acceleration. So we're going to take a streamline out of here. I'll take one over here maybe. So here's a streamline. And on that streamline, we're going to show a very small differential volume of, let's call it a liquid. So that picture, right? I'll draw the picture like it's in the textbook so you can follow it. Okay, so we have our little differential element. And let's see, we're defining delta S this way and delta Y, delta N that way. So here's delta N, here's delta S, and we have the weight of that little differential element acting down. And there's a pressure force on the left. So this is, the pressure in the middle is P, the pressure on the left P minus dP, multiplied by the area, dN dy. The pressure on the right side is P plus delta P dN dy. dN dy is the area over which the pressure acts. And I think that's all we've got in there in that direction, yeah. Let me make sure. Yeah, oh, let's get the angle theta. Get the angle theta. Here's the angle theta. We'll need that. So we're neglecting viscous effects, no viscosity. Otherwise, viscosity would act on these surfaces here. We're neglecting viscosity, so we'll put that down. We call that kind of fluid where we neglect viscosity, we call that an inviscid fluid. Inviscid. So if you see some words on an exam, you know what they mean. Inviscid, neglect viscosity. Incompressible, density's a constant. You can pull it outside the integral sign. Okay, inviscid fluid. All right, so let's write the sum of the forces in the S direction. And see, we have obviously two pressure forces left and right. But we know when we do this summation of forces that it's going to be mass times acceleration. Let's put that down first. Mass times acceleration in the S direction is equal to acceleration in the S direction up there. So we have delta M V dB ds. Okay, that's got that. Okay. And let's see, let's replace delta M with rho delta V. Don't forget, mass is density times volume. Mass is density times volume. Here's where I told you there's a V and a V slash. V means velocity, V slash means volume, differential volume. Multiplied by V dV ds. Okay. And for the weight, delta W, the weight in the S direction, minus delta W sine theta. That little guy right there is the component of the weight in the S direction. Notice which way it points, minus the sine. Okay. What's the weight? Gamma times the volume. So minus gamma delta volume sine theta. Component weight in S direction. The net pressure force. The net means subtract something. Net always means subtract something. So if we subtract this guy from this guy, the two pressure forces, subtract them, and we end up with delta F pressure force in the S direction. Okay. This guy minus that guy. The p's cancel out. Plus p minus p. Minus delta p minus delta p minus 2 delta p. Yes, that delta ps again just means in the S direction. You don't need to keep that subscript on there. So this then becomes replacing the delta ps, the 2, with this guy right here. Okay, that gives us that. Using this all right. Summation of forces equal mass times acceleration. What are the forces? The weight, the force due to weight in the S direction. The force due to pressure, net pressure in the S direction. So here's our components. Okay. So next step, put these guys all together. There's the weight. There's net pressure force. That's this left-hand side equals the right-hand side. There it is. You can replace V dV ds, the differential, 1/2 dV squared ds. dV squared ds is 2V dV ds. 2V dV ds times 1/2 is V dV ds, so they're the same thing. Finally, we get expression dp. Let dp come out of there. Multiply through by ds. Multiply through by ds. Cancels out, cancels out, cancels out. You're left with dp change. Move these two guys, right-hand side, plus dp. He's over there, 1/2 rho dv squared. Put him over the left, right-hand side, change the sign, gamma dc, there it is. So this is only valid though along a streamline. Back, what we did, we took a little fluid element along a streamline, like this. That little differential element had forces on it. Number one, gravity creates the weight in the s direction. So the weight, the component in the s direction, sine of theta. Okay, that's the weight. Acts down, minus sign, of course. The pressure acting on the left and right-hand faces of the element. Number one, call the pressure in the middle P. If you go in the negative S direction, that's towards me, of course the pressure is P minus dP. If you go in the positive S direction, that way to my right, then it's P plus dP. Multiply a pressure by an area. That gives you a force. If you take the difference in these two pressure forces, left and right-hand sides, it's going to give you a net pressure force. Net pressure force. So take this guy minus that guy, and you end up with this one. Use this guy in here. Okay. Delta PS right here. Put that in there. Okay, so net pressure force in the S direction. Weight in the S direction. With the equation, summation of forces in the S direction. Equal weight plus pressure. Equal mass times acceleration. This term is mass times acceleration. Redone in a little better format. Rho dV times velocity dV ds. Put all that stuff in the equation. Here it is down here. Play with it some more. Get it in a form that's useful. Get it in a useful form. That's our object. It's not in useful form yet. We're getting there. Make some changes here. This guy right here. Multiply through by ds. Put all the stuff on one side of the equation. There it is. Okay. We're almost there with Bernoulli. Okay, yeah.
What happened to the sine theta?
Oh, let's see, where does sine theta go?
Oh,
He's up here. Gamma, what did we do? Did I get that one right? Let's see if I got that one right. Sine theta dp ds. Over there we've got sine theta dp ds. Gamma dp ds. Oh, yeah. This is, let me put down, I didn't put this, it's in your textbook, but I'll put it on here. This is theta, that's the wrong way, pardon. This is ds. This is dz. This is theta. Okay. So sine of theta is what? dz over ds? Yeah. I'm going to draw one more. Okay. Here, here, here. dn, dz, theta. Cosine theta dz over dn. You can play those games to get rid of the sine theta. Okay, just go back and look at the geometry again. Yeah, thanks for mentioning that, Ron. Because it looks like it disappeared. It didn't disappear. I replaced it with a differential. Okay, now, obviously, we know what dp, dv squared, and dz. Next step, obviously, is to integrate. Okay, so we're going to integrate. Here's the terms we divide through by row. Divide through by row. dp over row, 1/2 v squared. Okay. gz, g's a constant, pull it outside. Call the constant c. When you integrate, we end up with a constant c. What's gamma? Rho times g. What do we divide by? Rho. Rho g divided by rho is what? G times z? Yeah, g times z. Integrate him, pull the half outside, pull the rho outside, divide by rho. B squared, that's where it came from. So C is a constant. Notice that this is written for a streamline. C has the same value anywhere along a streamline. Okay, so now we assume incompressible. Fluid. Rho equal constant. Pull rho outside, there goes sine. Okay. End up with P over rho. V squared over 2. G, Z equal to constant C. Every term has units, meters squared per second squared. The famous Bernoulli equation. It's a pretty straightforward derivation because it's inviscid. Later on, we're going to repeat this, but we're going to allow for viscous stress terms, where on the two top and bottom sides of this, that's going to be a lot rougher derivation. But this one is good a lot of times. You have to remember though, it's assumptions we pulled rho outside, incompressible. we said early on, inviscid, along a streamline, we didn't emphasize it, but of course it's for steady state. Okay, only apply Bernoulli's if those four assumptions are satisfied. Oh, there's an exception later on, but for right now, that's the four that we need. Okay, what's a streamline? Okay, right here. Lines that are tangent to the velocity vectors at every point in a steady flow field. So there's the word steady, okay. Steady flow field. Okay, so it applies along a streamline. That equation applies if you want to call this point 1, then you can call this point 2, and it'll apply along a streamline. Here's what you don't want to do. If that's point 1, you say, I don't like point 2 there. I'm going to put point 2 up there. Oh, no, you didn't read the board very well, did you? It says it applies along a streamline, not across a streamline. Not across a streamline. It applies along a streamline. So no, you can't do that. Point 2 has to be somewhere along that same streamline to apply the Bernoulli equation. Okay. Now, if I'm going to put this over here, because I want to save this middle panel for something else, so I'm going to erase this and save this space here. You can also apply similar kind of derivation, normal to the streamline, If you go through all those details, this is what you end up getting. This guy here, radius of curvature. It's more complicated because to integrate that second term, velocity squared divided by radius of curvature, dn, you need to know how both b and r vary with n. So that's normal to a streamline, that's along the streamline. Horizontal slope. What's R? Infinity. What's 1 over infinity? 0. If it's horizontal lines, that term drops out. That's the easy case. Easy case. Okay. Another form of Bernoulli's. Multiply through by rho. Okay. Rho times p divided by rho. Okay, rho's cancelled. 1/2 rho v squared. Okay. Rho times g. Gamma, rho times g, gamma. Units, pressure. Okay. Okay. All right. P by itself is called the static pressure. Rho v squared over 2 is called the dynamic pressure. Of course, it depends on velocity, so it's called dynamic pressure. Gamma times Z is called the hydrostatic pressure. This means hydrostatic. It depends on the height you are. We did this back in chapter 2. P plus rho v squared over 2 is called the stagnation pressure. The stagnation point in a full field is where the velocity is 0. Stagnate, 0 velocity, stagnation point. Let's see which equation I need here. Okay, now I need this board here. Now multiply by rho. Take the same equation, now divide by G. Okay, there it is. Divide by G, P divided by rho G. Oh, rho G's gamma. Let's go again. Divide by G, B squared divided by 2G. Divide by G, final Z. Okay. Box it in. Units, I'll take this guy, the third guy. Meters or feet. This is called the head farm of Bernoulli. P over gamma. Pressure head. V squared over 2G. Velocity head. Z. Elevation head. Okay, you got three different forms of Bernoulli equation. They're all the same equation, but they're just packaged in different ways. It depends the problem you've got, which one you want to use. If somebody asks you for the stagnation pressure, use the middle one. But it's up to you which one you use. Sometimes some are easier than others. If I know gamma of oil is 8,200, I'll use this guy. I won't try and get rho if I don't have to. So again, it depends on what's more convenient to you. But they are different. If you want to talk about the equivalent pressures, this guy talks about the equivalent pressure. Static, dynamic, hydrostatic, stagnation. You want to talk about the head form of the equation, the pressure head, the velocity head, the elevation head. And this was the one we derived, so. This has rho in it, this has rho in it, this has gamma in it. So it depends again which one you want to use. But no matter which one you want to use, for right now, these four things have to be satisfied. Okay. Incompressible fluid, inviscid fluid, steady state situation, and only apply it along a streamline. Okay, so let's take a look at a problem. Let me see if this edition or an earlier edition, 337. Let me find 337. Yeah, it's in our book, 337. So I'll do 337, put it over here. All right, here we have a tank which is pressurized. Let's see what that is. That comes out of there. Okay. Okay, and inviscid, this is what it says now. An inviscid, incompressible liquid flows steadily. First 6 words, major giveaway. An inviscid, incompressible, flows steadily. Okay. Yes, yes, yes. Not 3 yet. Not 3 yet. We'll get there. Okay. In this tank is a liquid. Gamma. Pressurized tank, air, pressure gauge, (10 psi). Velocity at the exit 40 feet per second. Uh, 16 feet, let me make sure. I've got 15 written down here. Check it, section. Let's see what we got. Oh, I'm sorry, 10 feet. 10 feet, 5 feet. So 10 feet from here to here, and 5 feet from here to here. Got it. Okay. What is the specific gravity of liquid in the tank? So find the specific gravity of the liquid. Okay. I could use any one of the three. I like to use that one, so I'll use that one unless there's a reason not to. So let's get rid of this one, and let's get rid of the other one, and we'll just leave this one on the board. The head form of the Bernoulli equation. Look at him. Okay. So, when you want to apply the Bernoulli equation, you're going to apply it between 2 points in the flow field. 2 points in the flow field. You want to choose those 2 points so that you know the most stuff about the problem. You say, okay, if I choose a point, can I find P, V, or Z there? And of course, I'm going to give you the obvious point first. I'm going to choose point 1 here. Why would I do that? Because I know what the pressure is. It's 10. I know what the velocity is. It's a free surface, 0. I know how far above the exit it is. It's 15 feet. That's how you decide where to put point 1, where you know the most information. So I'm going to write down that equation. Put the subscript 1. P1 over gamma plus V1 square root 2G plus Z1. Okay, now I go along a streamline until I find a point where I know some more stuff. Oh, I know this point down here is 15 feet below the free surface. Oh, I know the velocity here, 40 feet per second. Oh, I know the pressure here, it's 0. Voila. That's point 2. I know 3 things there. Now, there's the Bernoulli equation applied between points 1 and 2. All right, let's put the 0 stuff in first. P2, exhaust to atmosphere. Why do I know that? It shows in the picture. It shows the pipe ending and the velocity vector coming out of that pipe. That means you always assume in that situation that it's exiting to atmospheric pressure. Okay. P2, 0. I'm going to call Z2 0. That's my choice. That's called the datum. D-A-T-U-M. D-A-T-U-M. Datum, where you measure things from. If you're in a plant, a factory or a plant, the datum is typically the floor of the plant. How high is the water tank above the floor? 30 feet, etc., etc. So the datum, you're free to choose. You can take the top. I don't care. Take point 1. I'm taking point 2. How far above is point 1? How 15 feet? What's the velocity at 1? 0. The pressure at 1, 10 psi, 144, divided by what? Gamma of what? The fluid in the tank. Gamma, I don't know it. Equal. These guys are gone. 0 plus V2 squared. 32.2 plus 0. If you don't know G, always assume 32.2 or 9.81. That's a default value. Solve for gamma. 146.3. Remember what specific gravity is. It's your choice now. Here comes your choice. You can define specific gravity in terms of a density ratio or a specific weight ratio. Your choice. Take the easy way out. I just found gamma. I don't want to find a rho, so I'm going to use gamma. .34.
Once you know the specific gravity, you can usually determine the fluid that it is from the table, or okay.
You can go either inside front cover or back in the tables and look for SG and see what the fluid is. Yeah,
Okay.
yeah, exactly. Yeah. Oils are like 0.8, mercury's 13.6, water's 1, and then in between, you know, a ton of different fluids. But yeah, you can do a search. Yeah, pretty much forgot what's in that tank. Good point.
Right.
That's a good point. Yeah, yeah, that's right. Okay. I'm not going to start problem 2 right now. It's only got 8 minutes. I don't want to get halfway through and stop and pick up next time, so we'll do next time. Okay, I passed homework back. If you didn't get it, it's up here in front, over there. Homework is due right now on Blackboard. Homework all the way through the next Monday. Test in 9 days from today.